economic networks, about how we analyze economic networks, what are the metrics that we usually use to analyze economic networks. And I will speak specifically about the data that is available now, today. I will not make any presentation about myself like Christina did, because these 45 minutes that are for me will not be enough to go through the trajectory, how I got here, for example. So, but anyway, I work in Buenos Aires at this Network and Complex System Laboratory, where we work with the economic and financial networks, among all other things. So my first class would be about the introductory part. So I don't see anything, so I will be looking at my screen. Since I don't know about the backgrounds that you have, I don't know how many people are already working with networks and data. So this first class will be about the general introduction to the networks and the fundamental metrics that usually that we do have to know about the networks. And then I will speak about more precisely the economic networks and the appropriate network metrics that we have to know. So there is a very nice quote that I found. What would be the world without networks? So imagine a world where people have no friends, where roads never intersect, where computers are not interconnected. This world without networks would be a very sad and boring place where nothing happens. And even if something happened, nobody would know. Such a world is unimaginable because our life is completely defined by networks, relationships, interactions, communications, and the web. So since the internet came, everything had been changed. Biological networks governing the interactions between genes and our cells determine our development. Neural networks in our brain makes us think. Information networks guide our knowledge and culture. Transportation networks allows us to move. And social networks sustain our life. And this is a quote from the book by Menzer and Santo Fortunato and Clayton Davis. This is one of the books that I will be using in this course. And in particularly, social networks are the networks that mostly have been studied to extract the metrics that we use to study this kind of the topologies, to study the relationship between the nodes and the networks, and to study what the data brings to us as a knowledge. So before entering to the definitions and basics about the graph concepts, let me look at a few examples. And what's more, let me talk about the stories that these examples bring together. No? When I will explain each example, it's not just to show you what it is about, but each example will bring the notion of the concept, the notion of the dynamics, and the particular thing that I will speak along the 4 classes, and the particular thing that the networks have. Okay, so I bring the attention to this. And I chose in particularly 3 examples that have to do with the social network, with the infrastructure network that are power grid, and with the financial network. And then I will speak a little bit about the availability of the data. So we know very well what are the social networks, no? The social network is a group of persons that are connected by some type of the relationships. In particular, this relationship that connect 2 people, they are based on some sharing interests, no? That's how the states are defined. And there are many different types of social networks, no? For example, there are Facebook, there are Twitter, we have Instagram, and we have LinkedIn. So we know very well what each type of social network means. Me sale cierto, pero bueno. this kind of, networks, these are huge because they have lots of nodes, no? And we will speak about this. But also, we have small size groups, and these are also social networks. And for example, these have to do with the groups of with the networks that are very well studied in game theory. And I suppose that Marcelo will talk about this a little bit, because they have to do with the cooperation and coordination problems. And in particularly, it is well known that the group of 4 or 5 people, which may seem a very small and very negligible size, may cause a very huge coordination problem in game theory and in economics in particular, okay? So let me talk about the first story, yes? And I will speak, the first story, it's about a Twitter ego story, ego network. And what do I show here? Here we see a network that is, that comes from Twitter, yes? This is a very nice paper by an application of a graph-based approach to community detection in Twitter network. The author of this paper, he decided to verify a very interesting opinion that was at some moment circulating it in social networks, that was Twitter is very addicted, and it's very useless. So he decided to verify what happens to his proper Twitter network. So he used his followers, his Twitter network. So he built this network, and it's only the first step neighborhood, which means that he decided to download the connections of him, his followers, and the friends of the followers of his followers. So it's just the first neighbor structure. And he decided to analyze the tweets and the retweets of this network to decide how useful is his network, yes? And that's why it is called the ego network, because he decided to implement what is called the community detection, find community based on information flow. Along my classes, you will see that I always leave some kind of links with the information where you can find the information about each concept or each paper or each algorithm. So I leave the links with information at each step. So he decided to analyze each follower and the tweets and the topics. And what he found is, of course, what they do is to analyze the focal points, is the importance of each follower, of each user. And then it was a very interesting paper, because he classified the Twitter topic using spatial analysis. And he realized that the users, they organize because in a certain homophily way, because they organize in certain groups where they share similar characteristics. And for example, he found groups where he sees the people that are from this high school, or the people from a certain geographic area, and from his work, and where he speaks specific topics. So that's how he decided, he was extracting a very useful for him information, según the topics in each area. This is the second story, which has to do with a very interesting phenomena that happened in 2003. What happened in 2003? It was a blackout that left about 50 million people between US and Canada without light. at first glance, if we look at these two images, they seem to be the same, yes? But then, if we look a little bit closer, then we see that here we have, for example, we have Long Island, yes? We have Toronto, yes? We have Detroit. And now I can see, I can count like this 8 states that we don't have, that we are not seeing here, okay? So, and the dark, like this we can see the difference between this, after this inspection, yes? So, what we see here is that there was a blackout in 2003 because of the cascading failure, okay? Because if you want to know exactly what happened, this is the link, yes? And this system, it was vulnerability due to interconnectivity because there was an avalanche. Once one state failed, there was another state that failed. And this is like a power grid system once, because this is a very different network if you compare it to the social network. Because social networks, they are volatile networks. They can be changing the links in a very flexible way. If I don't want to be a friend of yours, I just cut the link and I will rewire it. The power grid networks, they are very static networks because even after the inspection of the topology, and if you find the problems, and if you, after the inspection you see that this topology is not an optimal topology and you find where are the problems, to infer in the policy making and to say that you have to make certain changes, it's not so simple because you cannot say that you have to move the station, and build another one. So, or you have to change the quantity of lines that transport the energy. So these are very different networks that have to be treated in a different way. So when we are faced with the cascading effect that why this kind of failures are happening? Because each node has a certain capacity that can absorb, and when there are a lot of energy that are passing through this node, which exceeds the limit of capacity, then it's break. And then this overload passes on the next nodes. And this is how the avalanche is producing, and that's how the nodes are failing. So when we are faced with the cascading effect, the magnitude of this cascading effect depends a lot on the position and the capacity of the nodes that are initially failed, okay? And this is the third example that already Christina showed, which has to do with the financial networks, yes? And why I bring it here, because the cascading failures have been observed a lot in the financial systems. And we have a very recent example that happened in 2008 when the Lehman Brothers failed. And I bring a lot this example. Why? Because the propagation phenomena happen a lot in financial systems because of the fragility or robustness of the system, of the financial system. But there are very interesting two concepts that take place in these networks. One has to do with too big to fail, and another too central to fail. And these two concepts have to do with the metrics of the node, with the centrality of the node. And this we will see when we start advancing with the course. Because each node has connections. So initially, people were thinking that when the node is too connected, when the bank has a lot of connections, then it is protected. Why? Because if there is a shock that's coming, it will be absorbed by the many banks, by the many connections that it has. And it's not true, because it has to do with the lots of different obligations that the other banks have. Yes, and that happened with what we observed in 2008. And then there was another another dynamics was proposed that has to do too central to fail, which has to do not only with the connections, but with the position of the node in the network. And this is what we will see in the class. Then there is another thing that is very important when we work with networks, which has to do with the availability of the data. And I think that we had this conversation in one of the Zooms. I remember that was your questions as well. How about the data that is available to study? Because we do a lot of models, and we build models, but the data is not always available. And here I show, for example, the data that is available. And for example, you can download any of this data and try to build the networks and try to analyze it. And for example, one of the sites that is called Stanford Large Network Data Collection. And here I have a snapshot of one of the possibilities that you have. You have a classification of the different large networks, data sets. For example, you have social networks, you have communication networks, you have citation networks, you have temporal networks, you have Twitter, you have road networks. So then when you enter here, you have different data sets with an information. You can download them and you can work with them. So this data, the good thing about this data is that it's already clean. So it's not the raw data. It's already adapted to work with. And then there is another thing that is called network repository COM. That also, it is classified, and you have different kinds of data. Here, for example, I work a lot with economic networks that has very good data available and for treatment. So I leave you with this slide so that you can, for hands-on, there are a lot of data to work with. Some few remarks about the data that is available on social networks is that, of course, it offers any scale and resolution. It also provides us with this opportunity to discover, track, to mine, and model what people do, but it also has a problem of ethics. Why? Because having this fantastic algorithm that we can scrap and we can enter to any kind of details and investigate whatever we want, then we do face a lot of ethic problems. So this is one of the things that we do have to keep in mind. And with economic networks, in this site that I show you here, these are some of the data that are available, but there are not a lot. Because in particular, it's usually a very private data. So it's very difficult to get an economic data. There are some public surveys. For example, in Argentina, we have an EPH, which is a survey of that periodically is actualized. And you have some access to this, but it's a very messy. So before one has to clean it very well. So this was like an overview to what kind of networks are and what kind of mechanisms happens on the networks. And now I will go quickly through the definitions and basic concepts. In my course, I will use these two books that are available online. So here you just click, because the slides are available, will be available, and you can enter. And this is a very nice book by Baravasi with very good exercises. And the book by Menser and the group, what is nice is that it has GitHub with a very nice Jupyter and Python developer and the codes. So you can download and work directly. So what are networks? So we work with these elements that the network has two parts. It has nodes, which are called nodes or vertices. You can call it network, you can call it graph. And it has a set of L. L is a pair of nodes that are called links or edges. So a link connects two nodes, I y J. Networks can be directed or undirected. A directed network also is called D-graph. In directed networks, links are directed. They have a connection. They have direction, no? Also, networks can be weighted y unweighted. Initially, and this is a very nice overview. I don't know if you know it, but this comes from a problem that in La Ciudad that is now called Kaliningrad, which is it's a city in Russia, pardon. There was a problem that there were 7 bridges, and the question was how to optimize to visit a city without crossing the bridge twice. So, and this problem was offered to find a solution, and Euler, at that moment, implemented the graph representation to show that this problem in particular does not have a solution because either of the sources or the target had to have in a node number of connections. So here I leave you also a link to see, there is a nice video how he was showing this. There are different types of networks, like Christina mentioned it, that we have a complete network, we have a random network, we have a regular lattice, which is which is studied in mostly, for example, in statistical physics, in mean field, etc. We have a bipartite graph. This type of graphs are usually studied in economics because we have usually 2 types of nodes. So these are connections between 2 types of nodes. For example, exportation between countries and which kind of products are exported by the countries. Or these are the matrices between the products and the insumos. ¿Cómo son insumos? ¿Ah? Sí. Insumo, producto. Products y resources. Sí. Entonces, how do we study the bipartite graphs? We need to do the projections. So we project each type of nodes using the relationships that this node have via another node. So for example, if I want to study the relationship between the countries, and if this bipartite graph represents the countries that export the products, so I do have to project the countries looking at how the countries have the relationship between them, looking at what products they relate between themselves, okay? And the same thing I can do if I want to study the network of the products. So I project at the level of the products, but then the products will be related via the countries. And then there is another networks which are called multi-layer networks. And this is a link where you can find a lot of information, because here we have not only different relationship between the nodes, but also we have relationship between different levels of the nodes. So what kind of network you can have here? This is, for example, Facebook, yes? But then in Facebook, you can have different friends, but also I can have friends of the primary school. And this is a Facebook of the primary school. But then also I can have friends of the secondary school. So this would be a different level of Facebook of the secondary school. And then I can go to my university. So this means that I am the same node, but then I have different kind of relationship that depends on if my friends belong to different colleges, okay? So what are the fundamental metrics that usually speak about that we look at the networks? First of all, when we look at the networks and we look at the large networks, we talk about density and sparsity, okay? So the maximum number of links will be always bounded by the possible number of distinct connections that we can have between the nodes and in the system. And if all the possible pairs of the nodes are connected, the network is complete. And here I leave you that depending if the network is directed or undirected, how we calculate the possible number of links. And then the density is just the relationship between the actual number of links with respect to the maximum number of links. And the same in the directed and indirected. And the important feature that helps in dealing with network structure is sparsity, which means that the fewer edges are in our network that we are considering, then the sparser is the network. Nuevamente, if the network is complete, then the density is 1, okay? Because they are all connected. And in the sparse network, the links are much less, the number of links, possible links, they are much less than the maximum number, so the density is much less than 1. The network is sparse if the number of links grows proportionally to the number of nodes, or even slower. And if the number of links grows faster, for example, quadratically, then we say that the network is dense. And it's interesting to take this example of Facebook, for example, that because it shows that the real networks, that the real world networks are usually sparse, in spite of the fact that they are very huge. For example, if we consider this example of Facebook, Facebook has around, it was in the year 2018, Facebook had around 2 billion users, yes? And if this was a complete network at that time, then there would be around 10 in the power 18 links, okay? But this is the number with 18 zeros. This, we cannot store this number, okay? In spite of that, Facebook doesn't have this kind of links because on average, each user has 1,000 friends or less. You see the difference? It's much less than 10 in the 18. So anyway, this is still a lot of data. And these are another examples of real networks. For example, this is, look at, these are IMBD. This is the data, this is the site of the International Movie Database. This is the Twitter. So here you can see those that are weighted and directed and undirected. Those where we see that there is a letter, these are the directed that have a direction. And where you don't see, these are undirected graphs. And here you can see the number of nodes, the number of links, and the density. And you can see that this real Wikipedia, US transportation, and you can see that these networks are quite sparse, in spite of the fact that these are really huge. So the following notions, these are what are really important in the analysis of the networks, yes? Because the networks can be analyzed in the following ways. When we have a network, we have nodes and we have links. This is what I just said. So the analysis of the networks can be done in two levels. You can put the importance on the nodes, or you can put the importance on the links. So if you want to put the importance and focalizar and to focus on the nodes, is because you look, for example, at the ego network, or you want to see, for example, what Pablo was explaining in terms of opinion formation. You want to see there are lots of applications who are the leaders or who plays the central role. So there are a lot of metrics that have to do with the centrality of the node. And we will see this kind of metrics. But then, if, for example, you look at the links, then what you want to see is the flow of information, for example, because the link, especially when it's not undirected and it has the direction, then it transmits something from one node to another. So for you, it's very important to see what are the direction, the corridors, where does it go, what are the density, the flow. So these are the two different analyses that one can make on the networks. These are the standard metrics that one has to know. One is the degree, which is K. K is degree of the node in the network, which is nothing but the number of connections. So you calculate how many connections the node has, okay? And this is different when the network is directed or undirected. Why? Because for a node which is undirected, it's just the sum of the connections that the node contains. But then when the network is directed, or when the node is directed, then it is important to distinguish between the nodes that are coming into the node, between the links that are coming into the node and between the links that are outgoing. And this is the difference how they calculate the K in or K out. The other important measure is what is called the average degree of a directed network. So which is the average sum, which is over all the nodes. This is, for example, it's just a simple example between how do we calculate. This is an undirected graph, and this is directed graph. And for example, these are the degree of the node, and this would be 0 because it doesn't have any connections. And these are, for example, the degree of the node. In the case it is undirected, it has 7 because it has in total, it has 4 because it has 4 connections, okay? Now, there is another notion of the node, which is called the strength of the node. What does it have to do, the strength? Because, as I said, that the networks can be weighted. So the link that connects the two nodes has the weight. The weight, for example, in financial networks, is the flow that comes from one bank to another, the credit. that is one bank gives to another. So it's the amount. So the link is, has the amount, has the weight. So how much flow enters that does have each link, this will define the strength of the node, yes? And this S is just the sum of all the strengths of all the flows that is coming to the node. In the same way, you can calculate for the directed graph. But in this case, you can have the difference, and you will have the difference between the ingoing and outgoing connections. In order to build a network, you have two representations. So you can have the adjacency matrix and you have the adjacency list. So this is just the way to represent the network. So adjacency matrix is just that through the matrix, if it has the 0 and 1, if it has connections or it doesn't have the connections. This is just a very expensive way of representations of the network if it has a lot of nodes. And the adjacency list is just the list of all the connections that the network has. And there is another thing that is very important is the degree distribution. And the degree distribution is what we really have to define because it defines a lot of properties of the network. So the degree distribution provides the probability that a randomly selected node in our network has a degree k. And so most of the network properties requires to know the degree distribution because it helps to determine many networks phenomena, from network robustness to, for example, propagation dynamics. So it's very simple to calculate when the network is very small, but then as the size grows, it's becoming a little bit more complicated. And here, for example, I show you the distribution of a real network. Here, it's a layout of the protein interaction network of East. So the nodes of this network correspond to East proteins. And the link between this network correspond to binding interactions. And what is interesting is that the degree distribution of this network, yes, it has this form. So, pardon? Is that power loss? Yes. So you can see here that the observed degree vary between 0 and here is 92. What does it say here, for example? It says that you can have isolated nodes, that's why it is 0, yes? And you can have the hubs, yes? So this is very important to know because not all the distributions show it. And the majority of the nodes, they have, they are here, yes? So this is a very important distribution, and we will see it later on. So another metrics that I want to show today, and with this I will not show anything else because all this is the clustering coefficient. So the clustering coefficient captures the degree to which the neighbors of a given node, yes, link to each other. So it is, for example, if I take a node E with a degree Ki, so the local clustering coefficient is defined like this. So I have to see how many, if the neighbors, my neighbors, have a link between them. So this is how I define the clustering. So what I look the triangles, if my neighbors form the triangles, okay? So when we look for the clustering, it's again, what I forgot to say is that the analysis of the networks also can be on a different levels. You can analyze at the local level, so you go to the level of nodes, you go to the level of links, and you can go at the global level, and then you look at the network as a global, as a macro. So you have a micro level and you have a macro level, yes? So, and then when I look at the macro level, then I look at the averages or at the global properties, okay? So, pardon. So, of course, I can have clustering 0 if none of the neighbors of a node, of a chosen node, are connected to each other. Which kind of network would be this? For example, a star. So I have a node, and I have connected a simple representation of this would be a star. None of the neighbors of mine are connected, okay? I can have a clustering 1 if the neighbors of node form a complete graph, because all of them are connected. So all of the, I can find all of the triangles, possible number of triangles. Clustering coefficient can be seen as a probability that two neighbors of a node can link to each other. So in this way, I can say that clustering of 0.5 would be 50% of chance that two neighbors of a node are linked, okay? And this would be a clustering coefficient. The average is nothing but the average of the sum of all the coefficients. Here I present you the further readings that are, I invite you to look at these books, which have to do with the things that I mentioned. And these are the metrics that I presented today, which are the fundamental metrics that everybody starts with when they look at the networks, okay? But I already mentioned that in order to analyze the networks, one has to look at the local structure or at the global structure. And I already mentioned that we have the centrality of the nodes or we have the importance of the links, yes? So I showed you that we have the problems of the propagations, we have the problems of fragility, yes? So this I mentioned because I started with 3 stories. So the idea of all this was that in the next class, I start with another story. And another story would be an economic network. So I presented here, I mentioned the financial network, but just passing by. So what would be the way to analyze the networks, which are the economic networks? Because they are different, okay? One of the main differences with economic networks is that they have a certain purpose because they have a different behavior, okay? They are very different from social networks, and we will see what is the analogy and what are the differences with social networks, okay? And I will present you the problem, which is the real economic problem. So we will start with a real economic network. And with this, I will show you the problematics. And starting from these problematics, we will start seeing what kind of metrics we really need to analyze this problem. Because these are the fundamental in order to see like the first glance of the network. But then we have a lot of different metrics, yes? And one can apply tens, 20s of metrics and start listing them. But then what does it give you? One can try to analyze and try to understand it. So the best way is to see what are the appropriate metrics for each type of network. Because there are some that are appropriate for social network, but these do not serve you for economic networks. Okay, this is the difference. So in the next class, I will show you that what are the appropriate metrics to analyze the economic networks. Okay, and that's how we start the next class. And for the hands-on, so my idea that we spoke with Marcelo and with Pablo is that my idea will be accomplish the exercises that they gave you. So obviously, no, it cannot be so far. So they propose you to extend, Marcelo, not yet, but I anticipate a little bit. So he proposed you to extend it to the network. So I will propose you to, as long as you start advancing, so you can start applying different metrics that I will be giving you and extracting more information. And tomorrow I will suggest you one paper which has to do with the financial network, and I will invite you to simulate it or to reproduce it. So it's a very simple model, very interesting model, so that would be an exercise. Okay, I will stop here.